A master builder faces a castle wall needing 10,000 identical stones. The sheer scale seems impossible, a collision of monumental ambition against the slow craft of the individual mason. This is the hidden story of medieval standardization, the revolutionary system that mass-produced our past. By the end, you will understand the precise, forgotten frameworks that built cathedrals and cities from chaos. How did a simple wooden template allow semi-skilled workers to shape history? And why were guild regulations the secret engine of this pre-industrial revolution? What does the relentless human drive to build big reveal about our own modern world? The master builder stares at the quarry, not at the rock space around it. He needs not a masterpiece, but a component. His challenge is one of pure mathematics, a problem of volume and time. To build that wall, he does not need 10,000 works of art. He needs 10,000 copies of the same, perfectly functional thing. This is the core tension that defined an era. For centuries, the stonemason was a sculptor. His chisel was an extension of his intuition, each strike guided by an eye trained over decades. The stone he shaped was a unique expression of his skill, fitting a specific, irreplaceable gap in a wall. The result was often breathtaking, a tapestry of individual hands, but it was also achingly, prohibitively slow. Imagine trying to assemble a vast mechanical clock where every single gear, every tiny pin, was filed to fit by a different artisan, each with their own idea of perfection. The mechanism would never run. This was the reality of construction before the Great Shift. A grand cathedral's arch, for instance, relies on a series of wedge-shaped stones called voussoirs. If each one varies even slightly in its angle or size, the arch's delicate balance of compression fails. The entire vault could collapse. Under the old model, producing 1,000 identical voussoirs was not just difficult, it was conceptually alien. The system was geared toward the singular, not the serial. Yet the drivers of the medieval world did not wait. Faith demanded taller naves to inspire the heavens. Kings demanded impregnable fortresses to secure their power. Growing cities demanded walls, bridges, and halls at a pace never before seen. The ambition was collective and colossal, but the method of realizing it remained stubbornly individual. This created an impossible bottleneck. The desire to build big was smashing against the ancient, respected craft of building small. Something had to give. The pressure was not merely logistical, it was existential for these monumental projects. They demanded a new logic, a way to translate a master's single brilliant design into 1,000 humble, interchangeable hands. The breakthrough would not come from a better chisel, but from a better idea. The skill had to migrate, lifting from the mason's muscle memory and being embedded into the process itself. This migration is where we find the birth of the template, the first great leap from craft into system. The template was a revolution in wood and iron. It began not with a grand decree, but with a simple, practical act. A master mason, after painstakingly calculating the perfect curve for an arch or the exact profile for a window frame, would not just carve that shape in stone. He would first carve it in oak. This wooden copy, this physical blueprint, became the true engine of construction. Think of it not as a tool, but as a teacher. It captured the master's years of accumulated knowledge, his intuitive grasp of load and line, and froze it into a single, tangible object. That object could then be handed to an apprentice who had been working for mere months. The instruction was beautifully simple. Make your stone look exactly like this wood. The complexity of the design, the fear of error, the need for deep geometrical understanding, all of that was absorbed by the template itself. The worker's task was reduced to a process of matching and removal, a repetitive act of comparison. This was the genius of the system. It separated the intellectual work of design from the physical work of execution. Suddenly, a quarry outside the city could be filled with teams of semi-skilled laborers, each with a wooden pattern for a specific type of block. One man might spend weeks doing nothing but shaping standard rectangular ashlars, the smooth-facing stones. Another, using a different template, would produce only the specialized wedge shapes for vaults. They did not need to understand why the wedge had that precise angle, only that their stone must match the guide. This created a kind of pre-industrial assembly line, but one spread across geography rather than a factory floor. A master architect in a capital city could design a cathedral, create a full set of templates for every single unique stone shape it required, and then send those templates out to multiple quarries across the region. Each quarry became a node in a distributed manufacturing network, all producing interoperable parts to the same exact specification. The stone for the north transept might be cut in one county, while the stone for the south aisle was cut in another. Yet when the carts all arrived at the building site, the pieces would fit together as if carved side by side. This was a profound shift. It meant that monumental scale was no longer limited by the number of master masons in one location. It was limited only by the number of workers who could follow a pattern. The template democratized precision, turning a rare art into a repeatable process. It was the first and most fundamental principle of medieval mass production, a physical idea that allowed a single brilliant mind to guide 10,000 hands. But the template alone could not build a city. A wooden pattern for one perfect stone solved the problem of copying, but what about the problem of combination? How do you ensure that 10,000 individually perfect components actually fit together into a coherent, soaring whole? The answer lies in a second, more abstract principle, the secret geometry hidden within the chaos of the scaffold. Medieval builders thought in modules. To them, a great structure was not a singular sculpture, but a magnificent assembly of intelligent, repeating units. This was modular design, and it was the logical mind behind the template's physical hand. Before a single foundation trench was dug, master architects would establish a governing proportional system. Often, this was based on simple, elegant ratios like 1:2 or 2:3, or the more complex but spiritually significant golden ratio. More practically, they would define a master dimension, a standard unit of measure like the rod or the perch, which might be 16.5 feet long. This unit became the DNA of the entire project. A wall's length would be a round number of rods. The height of a window might be exactly half the width of a bay. The thickness of a pillar could be a precise fraction of the nave's span. This was not arbitrary. It created a hidden harmony, a mathematical rhythm that the eye senses even if the mind does not calculate it. But its genius was profoundly practical. By designing with repeatable units, the builders created what we might call a catalog of parts. Think of it like a vast medieval kit. Once the master dimension was set, a specific type of stone block could be defined not by a unique description, but by a formula. Type A is a cornerstone, 1 unit long, half a unit high. Type B is a standard wall filler, 1 unit by 1 unit. Type C is a specialized vaulting rib, curved to a radius of 2 units. This modular thinking is what transformed quarries into factories. A quarry master, armed with the templates and the dimensional guide, could instruct his teams to produce not random stones, but batches of standardized components. They could cut 200 type A corner stones this month, 500 type B fillers the next, and stockpile them in yards. This was a logistical revolution. It meant a building site no longer had to wait for each specific stone to be custom ordered and slowly delivered. Instead, carts could arrive from multiple sources carrying interoperable parts, like pieces from the same immense puzzle. A mason on a scaffold high above the city streets would not receive a mysterious, one-of-a-kind rock and puzzle over its purpose. He would receive a clearly recognizable Type F window jamb stone, identical to the 50 others already in place. His work became less about interpretation and more about assembly. This modular system reduced on-site complexity to a staggering degree. It minimized errors, accelerated pace, and perhaps most importantly, it allowed for a separation of design and construction that feels strikingly modern. The architect could think in systems and ratios, the quarryman could think in batches and templates, the walling mason could think in sequences and placements. Each layer of the process was insulated from the others by the clarity of the module, turning the chaotic act of raising a mountain of stone into a manageable, almost rhythmic procedure. But who ensured that every quarry, every mason's lodge, every city across a kingdom was using the same rod, the same templates, the same catalog? The system needed a guardian, an authority to translate this brilliant logistical idea into universal law. That force was not a king or an army, but something far more pervasive in the medieval world, a network of power built on secrecy, skill, and strict communal rule. A wooden template is a silent teacher, but it needs a voice to command a kingdom. That voice belonged to the guilds. These were not mere trade unions or social clubs. They were the living memory and the iron will of medieval construction, the regulatory engine that turned clever ideas into universal law. To understand their power, you must see them as the guardians of what they called the craft's mysteries. This was not about magic, but about proprietary knowledge, the hard-won secrets of proportion, mortar mix, and structural integrity that distinguished a master from a novice. Protecting these mysteries was how a guild maintained its prestige, its monopoly on skilled work, and crucially, the quality of what was built. Standardization was their ultimate tool for this protection. Imagine a guild of master masons in a major city like Cologne or Florence. They would convene and, through rigorous debate and testing, establish the one true way. They would decide the approved dimensions for a standard brick, the exact ratio of lime to sand in mortar, the mandatory thickness for a load-bearing wall in a 3-story house. They created the rulebook. This rulebook was then enforced with remarkable rigor. An apprentice or journeyman working on a guild-sanctioned site was not free to improvise. If the template for a window mullion called for a specific profile, that was the profile you carved. To deviate was not seen as creativity, it was seen as a threat. It introduced weakness, inconsistency, and risk into a system that demanded reliability above all else. The penalties were severe. A mason caught using a non-standard brick size or an inferior stone might face heavy fines. For repeated offenses, he could be expelled from the guild, a sentence that was often economic and social ruin. He would be barred from working on any major project in that city or any other that recognized the guild's authority. This top-down control created something extraordinary, a common architectural language that could span hundreds of miles. Because the guilds were networked across Europe, communicating through traveling journeymen and shared apprenticeships, their standards began to align. A standard foot measure in Paris might be meticulously replicated in the Guild Hall of Vienna. This meant that a master architect trained in the French tradition could travel to Germany and understand the building blocks, literally and figuratively, of a project there. The materials and methods spoke the same technical language. This system reached its fullest expression when guild rules were absorbed into civic law. City councils, desperate to prevent the catastrophic fires that could sweep through tightly packed medieval streets, passed building ordinances that were essentially guild regulations writ large. An ordinance might mandate that all roof tiles within the city walls must be of a standard length and curvature to ensure proper waterproofing. It could specify that party walls between houses must be a minimum of 2 feet thick for fire resistance. It might even dictate the quality of oak to be used for main ceiling beams. Now, the template and the module were not just guild recommendations, they were legal requirements enforced by the city watch. This framework governed the entire supply chain, from the forester selecting trees, to the brickyard forming clay, to the quarry shaping stone, all the way to the mason on the scaffold. Every link in that chain was accountable to a written or universally understood standard. The result was a pre-industrial ecosystem of quality and compatibility. It meant a merchant building a warehouse in Hamburg could be reasonably confident that the bricks ordered from a nearby kiln would match the dimensions his carpenter had used to frame the windows. It turned the chaotic, localized world of medieval craftsmanship into a coherent, scalable system. But this system, for all its power, faced its greatest test not in the orderly guild hall, but in the unpredictable reality of the construction site itself. How did these perfect, standardized components handle the imperfections of the real world, the settling earth, the human error, the need for final adjustment? The true genius of the medieval builder was revealed not in the rigidity of the rule, but in a clever, flexible secret hidden within the joints. The true test of any system is not in the blueprint, but in the storm of activity at the worksite. To see the medieval standardization engine operating at its peak, we must step onto the muddy, bustling ground of a Gothic cathedral under construction. This was not a quiet place of prayer, it was a roaring, organized factory under open sky, a symphony of coordinated labor made possible by the rules we have just explored. Every principle of the template, the module, and the guild converged here into a single, breathtaking process. The journey of a single stone tells the whole story. It began miles away at a quarry humming with systematic purpose. Using the master architect's approved wooden templates, teams of workers were not carving unique sculptures. They were manufacturing identical parts. One team might produce only the slender, curved ribs for the vaults, another only the cylindrical drums for the columns, and yet another the intricate, pierced pieces for the window tracery. Each stone, as it was finished, received a crucial mark. Using a chisel, a worker would carve a simple symbol onto a hidden face, a letter or a geometric sign. This was the mason's mark, a pre-industrial barcode. It was not a signature of artistry, but a functional identifier, a number in an assembly guide. A stone marked with, say, a simple triangle might be designated as vault rib number 47 for the north aisle, bay 3. This small, chiseled symbol was the key to managing chaos. When cartloads of these numbered stones arrived at the cathedral site, they were not dumped in a random pile. They were sorted into organized yards, a kind of outdoor parts warehouse. Now, picture the site itself. Multiple teams worked simultaneously, often on different parts of the soaring structure. High on the rising walls of the choir, one group labored. On the opposite end, the foundations for the western towers were being laid. This concurrency was only possible because every team was working from the same set of standardized parts. A crane, often a massive treadmill-powered device called a great wheel, would be positioned for a specific task. Its design was refined over generations to efficiently lift the common weights and shapes the templates produced. The crane operator did not need to guess if the next stone would fit his rigging. He knew the standard blocks for this phase of construction were all within a certain manageable range. When the master mason on the scaffold called for a specific component, a laborer below would fetch not just any stone, but the correctly marked one from the yard. It would be hoisted, swung into place, and settled onto a bed of mortar. Because the stone had been pre-shaped to the universal template, it fit its neighbor with minimal adjustment. The mason's mark ensured it went exactly where the grand design intended. This was pre-industrial, just-in-time delivery and assembly on a monumental scale. The quarry produced to demand, the transport delivered in sequence, and the site consumed with precision. The cathedral rose not as a singular, slow-growing organism, but as a magnificent assembly of thousands of prefabricated, interoperable pieces. This system turned a project that might have taken centuries under the old craft model into one that could be achieved in a mere lifetime. The soaring vaults and forests of stone are a testament to a forgotten truth that the Middle Ages achieved a logistical and manufacturing sophistication we rarely grant them, building mountains of faith not just with pious hearts, but with brilliantly organized hands. That organized cathedral site was fed by a landscape transformed into a factory. The medieval quarry was not a chaotic pit. It was a carefully orchestrated production facility, the first and most critical link in a supply chain of stone. Its entire purpose was to turn a mountain into a mountain of components, and its methods were a marvel of pre-industrial engineering. The process began with reading the earth itself. Quarry masters were geologists by experience, seeking out stone with natural bedding planes, the lines of weakness where the rock had formed in layers over millennia. They did not simply attack the cliff face randomly. Instead, they used a technique called trenching, cutting deep, narrow channels around and beneath a massive block to isolate it from the surrounding stone. This was slow, deliberate work, often done with iron wedges and water, but it yielded a tremendous reward. Huge, rectangular blocks of predictable size and shape, pried from the earth like pages from a stone book. This initial extraction was the first act of standardization, creating raw material that was already leaning toward the geometric. The real transformation, however, happened right there at the quarry face. It was here that the wooden templates from the architect truly came to life. Workers, often semi-skilled laborers guided by a single master mason, would perform the first major shaping. Using the template as a guide, they would use heavy hammers and broad chisels to knock off the largest excess stone, roughing out the final form of the block or column. This process had a specific name, scappling. The genius of scappling was profoundly economic. Stone is incredibly heavy, and medieval transport was slow and expensive, whether by ox cart over rutted roads or by barge along rivers. Transporting raw, unshaped rock meant paying to move useless weight. By scappling the stone at the quarry, they could reduce its mass by a third or even half before it ever began its journey. The carts and barges were not hauling raw material, they were delivering semi-finished products, a fleet of rough sculptures all waiting for their final polish at the building site. This turned the logistics of supply into a calculation of efficiency, not just bulk, but the quarry's organization went even deeper. In a large, active quarry serving a major project, you would see a clear division of labor etched into the very terrain. The quarry master would designate specific zones for specific products, creating a kind of outdoor assembly line carved into the hillside. One section, where the stone was perhaps a bit rougher or more buried, would be dedicated to producing massive foundation blocks, the unseen giants that would bear the building's weight. Another area with access to finer-grained, more beautiful stone would be reserved for producing ashlar, those smooth, precisely squared facing stones that gave cathedrals and palaces their elegant skin. Yet another part of the quarry might be set aside for the specialized teams working on sculptural elements, like the pre-carved capitals for columns or the intricate pieces for window frames. This spatial specialization meant that tools, skills, and templates could be concentrated. A worker in the ashlar zone became an expert at producing one type of component, his movements becoming swift and repetitive, his eye calibrated to a single standard of perfection. The quarry itself became a three-dimensional blueprint, its different pits and shelves corresponding directly to the different parts of the rising structure miles away. The landscape was not just being mined, it was being read as a map of the future building, each extracted block already carrying the ghost of its final purpose. This systematic approach transformed the Earth's randomness into geometric order, long before the first stone was laid in its sacred or royal destination. A cathedral is more than its skeleton of stone. It is a skin of tile, a web of iron, a fabric of mortar. The true power of the medieval system revealed itself not just in the grand blocks, but in the humble, countless things that held them together. This was the third principle, a standardization that reached into every corner of the material world, creating an entire ecosystem of compatible parts. The star of the show may have been the soaring arch, but the supporting cast of brick, tile, and iron was just as rigorously rehearsed. Take the simple brick, a material of ancient origin that the Middle Ages perfected into a modular unit. The secret was the wooden mold. A brickmaker would press his wet clay into a four-sided wooden box of exact internal dimensions. When he lifted the mold away, he left behind not just a brick but a promise. That brick would be the same length, width, and depth as every other brick from that mold, from that workshop, and ideally from every other workshop following the guild's ordinance. This uniformity was not about aesthetics alone, it was about physics and efficiency. A standard brick allowed for predictable bonding patterns, like the classic stretcher and header courses that interlock a wall. More importantly, it allowed a mason to calculate mortar use with astonishing precision. He knew exactly how much lime and sand mixture he would need to lay 1,000 bricks, because the gaps between them were now a constant, not a variable. This turned bricklaying from an art of constant adjustment into a swift, almost rhythmic procedure of placement and buttering. The same logic governed the rooftops. A wooden form shaped clay into roofing tiles of a mandated curvature and overlap. Why? Because a roof is a system. If one tile is too flat, it pools water. If another is too curved, it creates a gap. But if every tile is identical, they nest together like scales on a fish, creating a continuous, waterproof shell over a vast hall. The city law that demanded standard tiles was not bureaucratic meddling. It was a collective defense against the chaos of leaks, rot, and catastrophic fire. The most telling extension of this system, however, was into the forge. Iron was expensive and labor-intensive to produce, yet it was essential. It took the form of nails to pin timber, cramps to lock stones together invisibly, and later, reinforcement bars to strengthen delicate tracery. As construction scaled up, the blacksmith could not afford to make each piece a custom fit, so the system reached him too. Builders began to design with standard iron sizes in mind. A typical joint detail in an architect's plan might specify the use of a 1-foot iron cramp, bent at each end to slot into pre-cut holes in adjacent stones. The blacksmith then could produce batches of these 1-foot cramps in advance, knowing they were a standard component for window frames or vault ribs. The stonemason, for his part, would cut his cramp holes to the standard depth to receive them. This is where the holistic brilliance of the approach becomes clear. The mason, the bricklayer, and the blacksmith were no longer independent artists solving isolated problems. They were specialists in a vast, distributed factory, all reading from different pages of the same technical manual. A standard brick was designed to work with standard mortar, which was gauged to set correctly around a standard iron wall tie. These were not separate inventions, but parts of an interoperable material language. This interoperability is what truly enabled mass production on a medieval scale. It meant a master builder could design an entire complex structure, a castle with brick infill, stone dressings, tiled roofs, and iron-reinforced gates, and have confidence that the components sourced from a dozen different specialized workshops would still fit together on site. The system reduced friction at every handoff, turning the monumental act of construction into a smooth assembly of proven, predictable parts. Yet, for all this mechanical precision, the buildings that resulted were not cold or sterile. They were alive with detail and grandeur. This leads us to the final, most human layer of the system, the delicate balance between the rigid rule and the creative hand, between the template's demand and the mason's secret signature. Yet within that vast factory of stone, a deeper, more elegant logic was at work. Geometry was the silent conductor of the entire symphony. It was not the abstract geometry of a classroom, but a living, practical craft, the shared language that allowed a master's vision to be communicated, broken down, and replicated across a continent. Every template, every modular ratio, every mason's mark was ultimately a child of this geometric thinking. The tools were beautifully simple: a compass for drawing perfect circles and arcs, and a square for ensuring true right angles. With these, a master builder could generate an entire cathedral from a single, foundational measurement. He might begin by setting the intended width of the nave, the central vessel of the church. This was not a random choice. From that one line, using the immutable truths of geometry, he could derive everything else. One of the most powerful relationships he used was the proportion between a square's side and its diagonal. If the nave's width is 1 unit, the diagonal of a square built on that width is the square root of 2, approximately 1.414. This irrational, seemingly messy number gave builders a ready-made ratio for setting the heights of arches or the dimensions of crossing squares. It was a proportional seed from which the entire organic form of the building could grow. This process was known as ad quadratum, or designing by the square. The builder would literally construct a series of overlapping squares and circles on his tracing floor, a large, flat surface of plaster where full-scale plans were laid out. Each intersection of a line, each radius of a circle, defined a critical point in the structure: the springing of an arch, the peak of a vault, the location of a pillar. The entire dizzying complexity of a Gothic rib vault was not invented stone by stone. It was born from the elegant rotation of a compass around fixed points. This geometric foundation is what made the system truly scalable and teachable. A complex window design with its delicate stone tracery forming flowing patterns looked like frozen lace. But to the master mason, it was a sequence of geometric operations. He would first establish the major circles of the design, then inscribe smaller circles within them, using their intersections to generate the pointed arches and flowing curves. This process could be recorded not as a subjective drawing, but as a recipe, a series of steps: circle A centered here, radius equal to line B. An apprentice could learn the recipe without necessarily understanding the profound mathematical harmony it created. This is where the medieval educational system, the quadrivium, whispers in the background. The quadrivium was the advanced study of the 4 mathematical arts: arithmetic, geometry, music, and astronomy. A master builder was often steeped in this tradition. To him, geometry was not separate from music or the movement of the heavens. The same divine ratios that governed a perfect musical chord were believed to structure a beautiful building and the cosmos itself. When he used a ratio like 1 to the square root of 2, he was not just solving an engineering problem. He was embedding the building with a hidden order, a resonance with a universe believed to be built on number. This philosophical layer gave the work profound meaning, but the practical outcome was sheer genius. It meant every single unique stone in that complex window, every curved rib in the vault, could be traced back to a geometric parent in the master plan. The template for each piece was not a standalone shape. It was a physical slice of a universal diagram. This is the ultimate key to medieval mass production. The system did not require 10,000 individual inspirations. It required one brilliant geometric conception, which could then be dissected into 10,000 reproducible geometric consequences. The mason in the quarry, following his wooden guide, was unknowingly executing a single step in a vast, silent mathematical equation written in stone. His chisel was solving for x, and this geometric rigor created a final, beautiful paradox: structures of breathtaking individuality and spiritual aspiration, born from the most systematic and repeatable process the pre-industrial world could devise. That geometric precision would have meant nothing if the stones never left the quarry. A perfect block is a monument to futility if it cannot travel. This was the next great challenge, one that forced the medieval world to innovate not in design but in movement. They had to build a supply chain. Think of a river barge, a broad, shallow vessel designed to carry immense weight on calm inland waterways. Its physical dimensions, the length and width of its hold, were not arbitrary. They became, in effect, a final, decisive template. A master quarryman knew the maximum block size his local barges could carry, and he shaped his stone to fit that floating box. Standardization met transportation in a perfect marriage of necessity. The stones were not just shaped for the building, they were shaped for the journey. This meant they could be stacked in the barge's hold like a three-dimensional puzzle, with minimal wasted space, turning each voyage into an exercise in volumetric efficiency. The same logic applied to the heavy, ox-drawn wagons that carried stone overland. Their beds were built to accommodate common lengths, allowing blocks to be loaded and unloaded using standardized ramps and levers. This was logistics reduced to a simple, repeatable procedure, a far cry from the chaos of moving 10,000 unique, irregular objects. Ports and loading docks evolved to match this new reality. You would see stone yards at river landings built with ramps at a consistent grade, and storage bays sized for the common unit. The material itself began to dictate the infrastructure around it, shaping the landscape of trade. Even the language of commerce adapted. The widespread use of the ton as a standard measure is a perfect fossil of this system. The word originally referred not to weight but to volume, the size of a large wine cask. It became a universal unit for shipping because it described a practical, manageable amount of space in a ship's hold. A merchant could contract for 20 tons of keen stone, and both he and the quarry master understood the approximate volume, and therefore the number of standard blocks that entailed. This created an integrated pipeline, a reliable conduit from producer to site. The wooden mold in the brickyard, the template in the quarry, the dimensions of the wagon bed, and the hold of the barge were all links in the same chain, calibrated to the same basic units of measure. This system's power is revealed in a transaction that would have been unthinkable centuries earlier. A master builder overseeing the construction of a great abbey in London could send an order across the English Channel to the famous quarries of Normandy. He would request by the ton a shipment of pale, fine-grained keen stone, prized for its workability. He could do this with absolute confidence. He knew the stones would arrive pre-shaped to the standards his templates demanded, ready to be lifted from the dock and placed directly into the rising walls, where they would fit seamlessly alongside the local Kentish ragstone. His project became a hybrid, a blend of materials from different kingdoms woven together by a shared technical language. This was more than construction, it was commerce and diplomacy in stone. The standardized component became a universal commodity, weaving a web of economic and cultural exchange across Europe. A cathedral could literally be a map of continental trade, its fabric telling a silent story of barges on the Seine, wagons on the Roman roads, and ships in the Channel. But this web of commerce points to a final, profound question. What did this relentless drive to systematize, to mass-produce the very bones of their world, ultimately do to the people within it? Did the triumph of the template extinguish the creative spark of the individual craftsman, or did it somehow, paradoxically, set that spark free? The mason's secret signature was not the only mark left behind. As the great building projects of the 13th and 14th centuries multiplied, a new kind of artifact began to circulate through the workshops of Europe, one that would capture the system's intelligence in a portable, revolutionary form. It was the pattern book. These were not grand philosophical treatises, but working manuals, the compiled notebooks of master builders. Within their pages, the oral traditions of the guild and the physical knowledge of the template were finally given a permanent, transmissible shape. They became the fourth and final principle, the codification of knowledge that allowed the medieval building system to think, learn, and evolve. The most famous of these is the sketchbook of a 13th-century French master known as Villard de Honnecourt. Its pages are a breathtaking glimpse into a master's mind at work. You will find no flowing prose, but a dense forest of diagrams. Precise geometric constructions for laying out a tower's footprint sit beside detailed studies of human and animal figures for sculpture. There are sketches of complex machinery, like a sawmill powered by a water wheel, and page after page of architectural elements, windows, arches, and pinnacles, each drawn with careful instructional lines. This was not a diary of one man's travels, though Villard claimed to have gone to many lands. It was a reference library and a teaching tool. A master could use these pages to show an apprentice how to derive the elegant curve of a window from a simple square and compass operation. More importantly, the book itself could travel. It carried the distilled technical solutions of one region the particular way French masons solved the problem of a flying buttress, or the preferred tracery pattern for a rose window across mountains and rivers to another. A master mason in a remote German town who might never set foot on the soil of France could now open Villard's book and understand the underlying geometry of Rheims Cathedral. He could replicate the design, adapt it to his local stone, and incorporate it into his own work. This transformed the pattern book from a personal notebook into a node in a continent-wide network of innovation. It was the software of medieval construction. Before, a brilliant technical advance might remain locked within a single lodge or guild, passed down slowly from master to apprentice. Now, that advance could be captured in a series of diagrams copied by scribes and carried by itinerant craftsmen to the next great project. This accelerated the evolution of style and technique at an unprecedented rate. The flamboyant Gothic tracery that blossomed in the 14th century with its sinuous, flame-like curves did not spread slowly from a single point of origin. It proliferated rapidly because its core geometric principles could be recorded, studied, and varied in these portable books. They created a shared visual and technical vocabulary that every educated mason could read. In a very real sense, these manuscripts were the first building information modeling systems. They did not just depict a pretty facade, they encoded the process of its creation. A single page showing a window might include the elevation, the geometric scheme for its layout on the tracing floor, and even notes on the sequence for cutting the individual stone pieces. It contained, in 2 dimensions, all the information needed to reproduce the 3-dimensional object. This allowed for a new kind of distributed design. An architect could now send a pattern book ahead to a quarry, instructing the workers there to begin producing components for a building he himself had not yet arrived to supervise. The book carried his authority and his technical intent. It ensured that when he finally reached the site, the parts waiting for him would be exactly as he had conceived them, even though they had been shaped by hands he had never met. This codification did something profound. It began to separate the idea of the building from the physical presence of its creator. The genius was no longer solely in the master's hands. It was in the pages of his book, a form of intellectual property that could be replicated and built upon. It turned architecture from a local craft into a transcontinental language, written in the universal alphabet of geometry and shared through the new technology of the codex. Yet, for all this systematization, the human element remained vital, for the system's ultimate purpose was not to create perfect copies, but to serve a society undergoing a profound and often painful transformation. The geometric diagrams in a pattern book were ultimately about more than beauty, they were about accounting. For every soaring arch and delicate window, there was a patron with a heavy purse, a king with a strained treasury, or a city council with anxious taxpayers. The true, unsung triumph of standardization was not artistic but economic. It transformed construction from a bottomless pit of uncertainty into a manageable, calculable investment. Before this system, funding a great project was a terrifying leap of faith. A lord commissioning a castle tower had to budget for the unknown. How long would it take a master mason to find and shape each unique stone? How much perfectly good rock would be chipped away and discarded in the process? The cost of custom craftsmanship was as variable as the weather and just as likely to ruin a carefully laid plan. The patron was essentially writing a blank check, hoping his funds would outlast the builder's slow, artisanal pace. Standardization changed this equation completely. By making the materials predictable, it made the finances predictable. A master builder could now perform a new kind of magic. He could provide a reliable estimate. He could calculate, based on his modular design, that the western facade would require, for example, 250 standard cartloads of facing stone, 100 cartloads of rubble for the core, and 40 pre-cut templates for the window groups. Each of these cartloads had a known market price, and each template represented a known amount of labor. The patron was no longer buying mystery, he was purchasing measurable units of progress. This predictability reached deep into the production process itself, systematically attacking waste. In a quarry operating under the old model, a mason carving a unique capital from a raw block might discard half the stone as useless chips and dust. But in the new, template-driven quarry, waste was recaptured. The large, off-cut pieces from scappling a major block were not thrown away. They were immediately assessed. Could this chunk be trimmed down into a standard wedge for vaulting? Could these smaller slabs be squared into tiles for flooring? The system created a hierarchy of material use, ensuring that almost every piece of stone, from the grandest ashlar to the humblest spall, had a designated, standardized purpose. This frugality was born of necessity. Stone was expensive to extract and far more expensive to transport. Wasting it was literally throwing money into the ditch. On the building site, this efficiency multiplied. With pre-shaped stones arriving ready for assembly, there was no need for a small army of highly paid master masons to perform final carving high on precarious scaffolding. Instead, the workforce could be tiered. A few masters oversaw the geometry and the critical placements. A larger group of journeymen handled the routine assembly. And the bulk of the labor, the hauling, mixing, and basic shaping, could be done by lower-paid, semi-skilled workers. By lowering the skill threshold for the majority of the tasks, the system dramatically reduced overall labor costs. It turned construction from a craft-centric art into a logistics-driven industry. This financial clarity is what made the medieval building boom possible. A bishop could now go to his chapter or a king to his parliament and present not just a glorious vision, but a viable business plan. He could say, for the pious sum of 10,000 gold crowns, we will receive a nave of this length, a tower of this height, and it will be completed within 7 years. The project was no longer a spiritual gamble, it was a bankable enterprise. This attracted investment on a scale never before seen, pouring wealth from royal treasuries, ecclesiastical coffers, and the rising merchant class into the construction of the very world we now call medieval. The cathedrals, castles, and city walls that dot the European landscape are not just monuments to faith and power. They are the physical dividends of history's first great revolution in cost control. This new economic logic reshaped the people themselves, forging a new kind of worker for a new kind of world. The cathedral site became a living diagram of specialization, a human reflection of the modular system it served. Gone was the romantic ideal of the solitary master who could envision, quarry, carve, and place a stone from start to finish. In his place stood a coordinated army of experts, each a master of a single, repeatable step. The quarryman knew the grain of the rock and the swing of the heavy hammer. The scapular, with his eye calibrated to a wooden template, could rough out a perfect block shape in a fraction of the time it once took. The foundation layer worked in the mud and the dark, concerned only with the absolute level and the immense weight of the plinth stones. Higher up, the wall builder focused on the rhythm of mortar and the alignment of faces, while the finisher, with finer tools, attended to the final dressing and detail. This was not a demotion of skill, but a radical redefinition of it. Proficiency was now depth, not breadth. An apprentice could enter the yard and within a year become remarkably adept at producing one specific type of standardized component, say, the cylindrical drums for columns. He did not need the decade of training required to understand the entire structure's geometry, only the precise movements needed to match stone to template. This accelerated the entire pipeline of labor. A steady stream of young workers could be fed into the system, trained quickly on their specialized task, and become productive contributors to the monumental whole far sooner than ever before. It was a division of labor that the economist Adam Smith would famously describe centuries later when observing a pin factory where one worker draws the wire, another straightens it, a third cuts it, each step making the total output soar. The medieval building site had already discovered this principle in stone. The result was a staggering increase in collective productivity. Teams could work in parallel without getting in each other's way because their tasks were distinct and their materials were predictable. While one group laid the foundation for the north transept, another could be raising the walls of the south aisle, and a third could be in the yard pre-assembling the complex window frames that would be lifted into place later. This concurrency, this ability to build in multiple directions at once, was the direct offspring of specialization and standardization. But this efficiency came with a profound social cost, one that quietly reshaped the community of the craft. A new hierarchy solidified, one centered less on individual artistic genius and more on one's function within the machine. At the top remained the master mason or architect, the keeper of the geometric mysteries and the overall systems designer. Beneath him were the wardens and foremen, managers who understood the sequencing and logistics of the specialized teams. Then came the journeymen, skilled in their particular trades like vaulting or tracery. And finally, the large body of semi-skilled laborers and apprentices, each a cog in a vast, beautiful, and impersonal clockwork. The identity of the worker was now intertwined with his position in the process, not with the uniqueness of his creation. The mason's mark, that chiseled symbol on the stone, is the perfect symbol of this shift. It was not a signature of pride in a singular masterpiece, but an identifier of accountability within a collective product. It asked not who made this, but which batch does this belong to, and who is responsible for its conformity. The system had begun to absorb the individual, trading the Renaissance ideal of the named artist for the relentless, anonymous productivity of the Gothic age. This tension between the collective achievement and the individual voice would echo through the stones for centuries to come. Yet the stone quarry was not the only birthplace of this revolution. Across the flat plains of northern Germany and the Baltic coast, a different landscape offered a different lesson. Here, the earth did not yield great blocks of limestone or granite. It offered clay, a soft, malleable material that would become the canvas for one of standardization's most elegant triumphs, the brick Gothic style. In this world without stone, the system did not adapt, it perfected itself. The wooden mold for bricks was not just a tool, it was an absolute dictator of form. From the rural monasteries that first mastered large-scale production to the urban brickyards that later supplied booming Hanseatic cities, the process was one of relentless duplication. They produced not thousands but millions of identical units, each one a perfect clone of the last, fired in colossal kilns that glowed like beacons of industry against the northern sky. This was mass production in its purest medieval form. the standard brick size, known as the format, became a universal building code, a ceramic currency accepted from Lubeck to Tallinn. But the true genius was not in the plain wall brick. It was in the specialized mold. Artisans created wooden forms for an entire catalogue of architectural components, all fired from the same local clay. There were curved bricks for the delicate ribs of star vaults, bricks shaped into slender columns for window tracery, and bricks molded with intricate relief patterns for decorative friezes that would run like ceramic lace around a church's facade. Imagine walking into a brick Gothic church in Stralsund or Malmö. Your eye is dazzled by the soaring height, the complex webs of vaulting overhead, the intricate patterns of the windows. The entire space feels like a symphony in terracotta, but come closer, run your hand over a pillar. You are not touching carved stone. You are touching dozens of pre-fired glazed bricks, each one a standardized segment of a cylinder locked together. That breathtaking rose window is not a single sculpted masterpiece, but a meticulous assembly of dozens of specially shaped brick types, each designed to interlock with its neighbors, each fired to the same exacting tolerance. The building is, in essence, a colossal, three-dimensional puzzle made from a finite set of ceramic pieces. This is where the system reveals its ultimate flexibility. By applying the principles of the template and the module to a material as obedient as clay, medieval builders could achieve staggering artistic complexity through the sheer repetition of simple, mass-produced units. A master designer could dream in a library of molded forms, knowing that each shape, once approved, could be reproduced by the thousand with no loss of fidelity. The kiln became the great equalizer, turning local mud into a limitless supply of perfect, durable, and beautiful parts. The brick Gothic cathedrals stand as a powerful testament to a profound idea that grandeur does not require rare materials or irreplaceable genius. It can be built from the most common earth, shaped by a communal system and assembled according to a shared plan. This was the democratization of the monumental, a vision built not from quarried privilege but from molded community. That ceramic puzzle of the North reveals a deeper truth about the system itself. It was never a prison of uniformity, but a language of construction, one with a rich and flexible vocabulary that could adapt to any local dialect of stone, wood, or earth. This is the fifth and perhaps most elegant principle, the adaptation to local materials and conditions. Standardization was not a rigid, one-size-fits-all dogma imposed from a distant capital. It was a brilliant, pragmatic framework that bent to the reality of the landscape. The goal was not to make every building look the same, but to make every building process work the same way, regardless of what the earth provided. So the system learned to speak in timber, in flint, and in rubble. In the great forests of England and Central Europe, where oak and pine were plentiful but good building stone was scarce, the carpenter became king. Here, the principles of the template and the module were translated from stone into wood. Carpenters developed a catalogue of standardized joint types like the mortise and tenon, a tongue and groove connection that could be cut with precise, repeatable templates. They perfected structural frames like the mighty cruck frame, where two great curved timbers were joined at the peak to form an arch, or the box frame, a grid of posts and beams. The genius was in the prefabrication. These complex timber skeletons were not assembled in the air, high on a wobbly scaffold. They were laid out and joined on the ground, in the carpenter's yard, where every cut could be checked against a pattern and every joint tested for fit. This was assembly line thinking applied to trees. Once a frame was complete, the entire community would gather for the raising. With ropes and poles, they would lift the pre-made wooden skeleton into position on the stone foundation, locking it together with wooden pegs. In a single dramatic day, the bones of a great hall or a barn would stand against the sky. The house was literally raised from the ground up, a testament to planning and precision. The system adapted just as cleverly in regions with poor stone. In areas like East Anglia in England, where the land yielded only hard, knobbly flint nodules or irregular rubble, the master builders developed a brilliant two-part strategy. The standard here became the module of the facing stone. They would create a smooth, decorative skin for the building using whatever small, attractive stones they could shape or find, often set in intricate patterns. But behind this handsome facade, the core of the wall was a different story. It was filled with a chaotic mix of rubble, broken bricks, and any other cheap, durable material, all bound together with a vast quantity of strong mortar. The craftsman's skill lay in creating the wooden formwork, the temporary mold, that would hold this loose core in place while the mortar set. The facing stones were the standardized, visible product, the public face of order. The rubble core was the pragmatic, invisible reality, accepting local imperfection but containing it within a disciplined shell. In every case, the underlying principle held firm: create repeatable, predictable elements from whatever material is at hand. This local adaptation had a beautiful cultural consequence. It prevented the medieval landscape from becoming a monotony of identical buildings. The disciplined framework of systematic production did not erase regional identity. It gave it a structured way to express itself. A cathedral in the limestone belt of France soars with delicate, glass-filled tracery made possible by its excellent stone. A guild hall in the bricklands of Poland presents a fortress-like solidity and a vibrant palette of glazed ceramic patterns. A tithe barn in the English countryside stands under a breathtaking timber roof, a forest of oak translated into architecture. They all share the same hidden logic of templates, modules, and pre-planned assembly, yet they look and feel utterly distinct, born from their place. This proves a powerful point about rules and creativity, that a strong, shared system does not stifle originality. It can actually foster it by solving the basic problems of how to build, freeing the community to express who they are and what they value within that reliable framework. The local stone, the local tree, the local clay, these were not obstacles to the master builder's grand vision. They were the very ingredients of its expression. But this elegant, adaptable system, for all its success in raising monuments, was about to meet a challenge it could not simply build its way out of, a force that would test the very social fabric it had helped to weave. A king's power could be measured not in gold but in days. When a new territory was seized, the clock began ticking. Local resentment simmered, rival lords eyed the prize, and rebellion was a constant threat. The most potent symbol of control was a castle rising on the horizon, but if that castle took 20 years to build, it was a monument to futility. The king needed it now. This military imperative became the ultimate driver of construction standardization, forging the principles of the template and the module into instruments of pure, rapid dominion. The castle, often romanticized as a unique fortress of individual genius, was in many ways a mass-produced tool. Its design evolved into a catalogue of reliable, interchangeable parts, each honed by the brutal logic of warfare. Consider the arrow loop, that narrow slit in a thick wall. It was not a random crack. Its precise form, with a widened interior to give an archer room to aim and a narrow exterior to protect him from incoming fire, was a masterpiece of defensive geometry. Once perfected, that shape became a standard template. A mason anywhere in the kingdom could be given the wooden pattern and produce identical loops for 100 towers, ensuring every defender had the same optimal field of fire. The same went for the tooth-like merlons atop a battlement. Their height, width, and the spacing between them were calculated to provide maximum cover for soldiers. These measurements were codified, turning the castle's crown into a repeatable, off-the-shelf component. Even the terrifying machicolations, those stone galleries over a gatehouse with holes in the floor for dropping stones or hot oil, followed a standard design. Their corbels, the supporting brackets, were often pre-cut to a common profile, allowing them to be slotted into place quickly during construction. This modular approach extended to the largest elements. The cylindrical keep, a towering drum of stone, became a preferred typology across Europe from Wales to the Holy Land. Why? Because its curved walls were better at deflecting siege projectiles than flat ones, and its circular interior simplified the layout of supporting vaults. But its greatest advantage was logistical. A master architect could draw up one perfect cylindrical tower plan, and that single set of templates could be used to build a dozen identical keeps across a frontier. The local laborers, guided by those templates and using stone from the nearest quarry, could erect a formidable stronghold in a matter of months. This was the system's ultimate expression of power. A king like Edward I of England, conquering Wales in the late 13th century, did not have to invent a new castle for each valley. He had a repertoire. He sent his master mason, James of St. George, with a portfolio of standard designs for gatehouses, curtain walls, and drum towers. Teams of workers, many recruited locally, then executed these plans with factory-like efficiency. The result was the Iron Ring of castles around Snowdonia, a defensive network built with astonishing speed. Conwy, Harlech, Beaumaris, these were not slowly evolved family homes. They were prefabricated instruments of state power, stamped into the landscape to quell a region. This rapid consolidation was only possible because every element, from the murder holes above the gate to the shape of the latrine chute, was pre-thought, pre-designed, and reproducible. The castle became a kit of parts, a terrifyingly efficient machine for control, assembled from 1,000 standardized components. Its walls were not just barriers against armies, they were the physical manifestation of a new, systematic way of imposing order, proving that the most enduring power is often the kind that can be built at speed. But a castle built in haste is only as strong as its weakest stone. The sheer speed of this modular production introduced a terrifying new risk, the hidden flaw. One cracked block, one poorly angled voussoir, could bring a tower down upon the heads of the very men it was meant to protect. In a system built on anonymous output, how could you ensure that every single one of 10,000 components was made with care? The answer was etched into the stone itself, a simple chisel mark that carried the weight of a career. The mason's mark was the soul of the system, the human fingerprint on the age of mass production. It transformed a block from a mere commodity into a named responsibility. When a mason finished shaping a stone to its template before it left his bench, he would take his chisel and carve his own unique symbol into a hidden face, a simple geometric design, a letter, or a stylized tool. This was not an artist's signature seeking fame. It was a craftsman's identifier accepting accountability. That mark made the stone traceable. It was a permanent record, a medieval barcode that linked the finished product directly back to the hands that made it. Imagine the scene at the building site when a stone destined for a critical arch arrived and upon inspection had a hairline fracture. Under the old system, the fault was collective, a vague failure of the process. Now the master builder could turn the stone over, find the mark, and consult his ledger. The flaw could be traced back to a specific mason, or even to a specific week's output from a particular quarry team. This created a powerful and direct feedback loop of quality control. A worker knew that his mark, and therefore his reputation, was literally being built into the wall. If his stones consistently fit poorly or showed weaknesses, the master would know. The consequences were not abstract, they were professional and financial. Guilds, the guardians of craft standards, took these marks with utmost seriousness. A mason standing within the guild, his eligibility for better wages, and his prospects for future work were all tied to the reliability of the products bearing his symbol. A record of poor work could lead to fines, demotion, or even expulsion from the guild's protective network, a sentence that meant economic ruin. This simple tool ingeniously solved the core dilemma of industrial scale work: how to maintain individual care within a collective, repetitive process. It embedded a powerful personal incentive into the heart of the assembly line. The drive for quantity, fulfilling quotas to meet the relentless pace of construction, was now balanced by the sobering knowledge that each piece would carry your name into eternity or into the rubble. This system of marks ensured that standardization did not become an excuse for shoddiness. It forced the abstract concept of structural integrity down to the level of the individual worker's pride and livelihood. The magnificent structures that have survived the centuries do so not just because of brilliant geometry or strong mortar, but because the man shaping the seventh wedge stone for the north vault knew that if it failed, everyone would know it was his. That quiet, daily pressure, chiseled into a million hidden faces, is a silent testament to the human element that truly made the system stand the test of time. Yet that same mark, a symbol of individual accountability, also points to a greater collective freedom. The rigid reliability of the standardized component became, paradoxically, the very foundation for breathtaking architectural risk. Once a master mason knew he could count on 10,000 identical, perfectly fitting stones, his mind was liberated to solve the one problem that truly mattered: the next great leap. This is the hidden engine of the Gothic Revolution. The flying buttress was not just a beautiful stone arch, it was a structural epiphany, a way to channel the crushing weight of a vault outward and downward, freeing the walls from their load-bearing duty. Before standardization, such a concept would have remained a fragile sketch on a tracing floor, too dangerous and complex to execute at scale. But within the new system, the moment the principle was proven, the innovation could be industrialized. The master and his geometricians could dissect the elegant curve of the buttress into its constituent parts: the sloping pier, the arched flyer, the sturdy pinnacle. For each part, they carved a new wooden template. These templates were then sent to the quarry, where teams began mass-producing these novel components as if they were simple wall blocks. The revolutionary idea was, within a season, reduced to a repeatable manufacturing process. This is why the Gothic style did not simply spread. It exploded across Europe with a speed that still stuns historians. A solution perfected in the royal workshops of the Isle de France could be templated, recorded in a pattern book, and carried by a traveling master to the Rhineland or to England. There, local builders did not need to reinvent the wheel, or more precisely, the arch. They received the geometric recipe and the physical templates, and their quarries began outputting the parts. The local masons then assembled this imported innovation using the same familiar techniques they employed for every other wall and window. The risk of the entire daring enterprise was thus contained. The architect was gambling only on his new structural idea, not on the competence of his workforce to execute 10,000 unique carvings. The building's entire fabric, the vast bulk of its stone, was composed of reliable, predictable units. This allowed for a series of spectacular experiments in the pursuit of light and height. Builders could push the limits of how thin a wall could be because they knew the millions of stones within it were uniform and strong. They could design ever larger windows filled with complex tracery, confident that the pre-cut pieces would lock together precisely. The cathedral became a kind of laboratory where the stable, mass-produced background allowed the brilliant, singular variable of a new design to be tested safely. The system did not standardize creativity out of existence. It created the stable platform upon which creativity could safely perform its most daring leaps. The soaring vaults of the Gothic age were not born in a vacuum. They were raised upon the silent shoulders of a fallen giant. The sixth principle underpinning medieval standardization was not an invention, but an inheritance, a legacy of Roman precedent. For centuries after the empire's political collapse, its physical bones remained scattered across the landscape. A medieval mason did not need a history book to understand Roman engineering. He simply needed to walk outside his town. There stood a crumbling aqueduct, its arches still defiant. There lay the ruins of a villa, its floor a mosaic of countless identical baked clay tiles. The Romans had been the undisputed masters of systematic construction on an imperial scale. They had perfected the mass production of fired bricks, stamping them with the mark of the legion or the workshop that made them. They had developed concrete, a revolutionary material that could be poured into wooden forms to create vast, standardized structures like the dome of the Pantheon. They used metal clamps, often of lead, to lock giant stone blocks together, a technique for prefabricating strength. This was a civilization that thought in terms of networks, of roads, forts, and cities built from interchangeable parts to facilitate rapid expansion and control. Much of the deep technical knowledge behind these feats, the precise recipes for mortar or the administrative systems that managed distant quarries, did fade in the early medieval period. But the ruins themselves were an open-air library, a constant, tantalizing reminder of what human organization had once achieved. Medieval builders became reverse engineers of a lost world. They would examine the walls of an old Roman fort, noting the consistent size and bonding pattern of the bricks. They would study the modular floor plan of a basilica, recognizing how its repetitive bays and columns created a flexible, grand space. A master mason contemplating the rounded arch of a Roman gate was not just seeing an old doorway, he was studying a solved problem, a proven geometry for spanning space. This physical evidence taught a powerful lesson that monumental, durable construction was not magic, it was a system. The medieval drive for standardization was in part a conscious effort to recapture that lost logistical and engineering prowess. They saw in those ruins a mirror of their own ambitions to build big, to build fast, and to build to last across a fragmented world. But this was not mere imitation. The medieval world was fundamentally different. The unifying force was no longer an emperor in Rome, but the Christian church spread across diverse kingdoms. The economic engine was not imperial taxation, but feudal obligation, merchant wealth, and pious donation. The social structure was not a centralized bureaucracy, but a patchwork of guilds and communes. So when medieval builders reached back for Roman wisdom, they filtered it through their own reality. They adopted the Roman idea of the module, but used it to design cathedrals that reached for heaven, not basilicas for imperial administration. They embraced the concept of standardized parts, but produced them through guild-regulated workshops, not state-owned factories. They saw the value of infrastructure, but built it for pilgrimage routes and fortified market towns, not for legionary marches. The result was a unique hybrid, a fusion of ancient systematic thinking with medieval spiritual aspiration and local pragmatism. The Roman Precedent provided the foundational confidence that such scale was possible, while the medieval context demanded the new, flexible systems of templates, pattern books, and guilds to achieve it under entirely new conditions. This quiet dialogue with the past, this reverse engineering of ruins, gave the Middle Ages not a blueprint to copy, but a catalyst for their own revolutionary chapter in the story of how we build. That dialogue with the Roman past taught more than just technique. It taught a profound respect for the materials themselves. The medieval system of standardization, for all its drive toward speed and scale, developed an unexpected but powerful consequence, a sophisticated form of environmental and resource management. In a world without fossil fuels or global supply chains, every block of stone, every load of timber, represented a colossal investment of human and animal energy. Wasting it was not just inefficient, it was a direct threat to the project's viability. The system's precision became its greatest conservation tool. By designing with exact modular sizes and cutting stones to precise templates, builders dramatically reduced offcuts and spoil. A mason roughing out a standard ashlar block at the quarry knew exactly how much stone to remove, leaving behind a usable block and a pile of smaller, but still valuable, rubble for wall cores or road foundations. This careful calculus of material extended the life of a quarry itself. Instead of haphazardly gouging out the landscape, quarry masters worked in orderly benches and trenches, following the natural bedding planes of the rock to extract the maximum number of usable blocks from a single site. A well-managed quarry could supply stone for generations, becoming a sustained local resource rather than a quickly exhausted scar. This logic of conservation created a circular economy of stone that still shapes European cities today. Because stones were cut to common dimensions, they possessed a kind of architectural immortality. When a castle fell into disuse or a monastic complex was dissolved centuries later, its materials did not become worthless debris. They became a pre-cut inventory for the next era. The stones of a demolished Romanesque church, with their familiar, standardized shapes, could be easily cleaned and reused in the foundation of a new Gothic market hall. A fortified town wall, no longer needed for defense, could be carefully taken down, and its perfectly good-facing stones could become the fabric of a row of merchant houses. This practice was so widespread that many medieval city centers are, in essence, vast palimpsests of reused stone, each block carrying the memory of multiple structures across time. The system's very uniformity granted materials a second, third, or fourth life, a sustainable loop that modern construction, with its bespoke components and bonded composites, often struggles to replicate. Beyond the stone itself, the system's efficiency minimized broader human and ecological disruption. A project that might have dragged on for a century under the old craft model, with its constant demand for labor and its permanent encampment of workers, could now be completed in a few decades. This meant a shorter period of intense pressure on local food supplies, forests for fuel and scaffolding, and the community drafted for the back-breaking work of haulage. The landscape around a building site was not subjected to a century of exploitation, but to a concentrated, well-organized burst of activity. Once the last template was put away and the final mason's mark was covered by plaster, the land could begin to recover, and the local population could return to the rhythms of farming and trade, their lives no longer defined by the endless construction of a single monument. This balance between colossal ambition and local limits was not a conscious environmental policy, but a hard-won pragmatism. The medieval builder, operating within the strict energy budget of the pre-industrial world, had no choice but to build sustainably. His standardized system was the ingenious tool that made such restraint not only possible, but spectacularly productive. It allowed society to raise its grandest dreams without consuming the very ground upon which they stood. The master mason's ledger was more than an account book, it was a passport to a new world. This individual, once merely a highly skilled carver, now emerged as a pivotal figure, a literate and numerate technical manager. He could read complex geometric plans, calculate material quantities down to the last cartload, and manage budgets that rivaled those of minor nobles. His expertise, rooted in the universal language of the template and the module, was transferable across kingdoms. Consequently, his wages soared, and his social status blurred the rigid lines of the feudal order. He answered not just to a local lord, but to a bishop, a city council, or a king. His authority derived from knowledge, not birthright. This created a new professional class whose power was built on the systematic intelligence of the building yard, a quiet but profound shift in the medieval social landscape. These yards themselves became some of the most dynamic spaces in Europe. A cathedral worksite in, say, Chartres or Prague was a bustling, polyglot community. You would hear dialects from Cornwall to Cologne, see techniques from Lombardy being adapted by masons from Normandy. A master glassworker from France might collaborate with a German specialist in lead cames, while a local carpenter learned new jointing methods from a traveler from the Baltic. This constant circulation of craftsmen turned each major project into a living university of technique and style. Ideas did not travel in scrolls alone, they traveled in the muscle memory and practiced eyes of these itinerant builders. A novel way to brace a roof truss or a fashionable new tracery pattern could spread across the continent within a generation, carried not by armies, but by journeymen seeking the next great project. This cross-pollination on the scaffold forged a shared European culture of making, one that transcended political borders and local dialects. The most visible impact of this system, however, was etched into the skyline of every growing town. Walk through the center of a preserved medieval city like Strasbourg or Bruges. You are not surrounded by a chaotic jumble of unique artistic statements. Instead, you see rows of timber-framed houses where the spacing of the beams follows a familiar rhythm, or streets of brick townhouses where the proportions of windows and gables speak a common language. This cohesive urban aesthetic was no accident. It was the direct, democratized product of material standardization. Local building ordinances, often based on guild rules, dictated standard beam sizes, roof pitches, and even the alignment of upper stories. The wealthy merchant's house and the humble artisan's workshop were built from the same catalogue of standardized parts, just arranged with different levels of ornament. This created a visual harmony, a streetscape that felt ordered and intentional. From the cobblestones underfoot to the tiles on the roof and the bricks in the wall, the medieval city became a physical manifesto of communal life. The same systematic thinking that produced a cathedral's vault also produced a market stall's awning frame. This shared architectural vocabulary, spanning from cottage to cathedral, did something profound. It visually reinforced the structures of medieval society itself. The ordered facade of the street mirrored the desired order of the community. The sturdy, reliable timber frame of a house echoed the ideal of a sturdy, reliable household. The towering church, built from countless identical stones, stood as the ultimate symbol of a unified faith. The system that mass-produced buildings, in the end, helped mass-produce a sense of place, identity, and belonging, wrapping the complexities of medieval life in a recognizable, reassuring shell of geometric order. The stone cathedral, for all its geometric perfection, could not carve its own saints. This reveals the seventh and final principle, the inherent limits of the system. Medieval standardization was a logistical marvel, but it was not a magic wand. It excelled at producing the repetitive, the structural, the countless identical parts that formed the body of a building. Yet the soul of the structure, the expressive heart, always lay beyond its reach. Look up at the facade of a great Gothic cathedral. You see a forest of identical columns, rows of matching windows, and armies of uniform pinnacles, all testaments to the template's power. But then your eye is drawn to the central portal where a crowd of stone figures gathers. Here is a solemn apostle, there a smiling angel, each face bearing a unique expression, each fold of their robes flowing with individual life. These were not the work of a laborer with a template. They were the creations of master sculptors, artists whose skill could not be reduced to a wooden pattern. Their work was slow, deliberate, and irreplaceable, the one part of the process that defiantly resisted mass production. The same was true for the most complex intersections of vaults in a chapter house, or the intricate, non-repeating bosses that crowned the meeting of ribs overhead. These nodal points of incredible structural and artistic complexity demanded the direct, intuitive hand of a true master, a living library of geometry and craft. The system was designed to build the stage, but it still needed singular artists to perform upon it. Even within its own domain of repetitive parts, the system was not flawless. Its quality was entirely dependent on the local materials and the rigor of the guild enforcing the standards. The fine, creamy limestone of Burgundy could be cut to a tolerance that the coarse sandstone of a remote northern region might struggle to match. A brick from a well-regulated urban kiln, fired for days in a consistent heat, was a world apart from one produced hastily in a rural clamp kiln. When supply chains stretched over hundreds of miles, this variance could become a problem. A master builder might receive a shipment of ashlar blocks that were technically the right size, but of a subtly different grain or color, creating a patchwork effect in his perfect wall. More critically, those long supply chains were the system's vulnerable arteries. A castle under construction in a contested border region might find its supply of specialized stone completely severed by a sudden siege or the movement of armies. A harsh winter could freeze the rivers that barges depended on, stranding vital materials at a distant quarry. The entire elegant network of quarries, carters, and bargemen was a peacetime luxury. It required stable roads, secure waterways, and predictable markets to function. When that stability shattered, the system shattered with it. This fragility points to the ultimate limit, one not of engineering but of society. The medieval building machine did not operate in a vacuum. It was a delicate ecosystem that required a specific climate to thrive, a climate of relative social order, economic surplus, and demographic stability. The great crises of the 14th century delivered a catastrophic shock to this climate. The outbreak of the Black Death, the pandemic that swept through Europe, did more than cause immense loss of life. It ruptured the very fabric of the workforce. Guilds lost masters and apprentices in staggering numbers. Quarries and transport routes were left without enough strong hands to operate. The intricate knowledge passed from master to journeyman faced erasure. Projects that had been humming with activity for decades, like the Cathedral of Siena, were suddenly frozen, their grand ambitions halted mid-air by a scarcity of labor so profound it reshaped the continent's economy. Following this, the prolonged conflicts of the 100 Years' War between England and France consumed treasure and lives, redirecting resources from construction to destruction. The stable trade routes and royal treasuries that funded monumental projects were drained or severed. The networks of trust and contract that allowed a master in Paris to order stone from Normandy collapsed into the chaos of warfare. In such times, the system of standardization did not gradually slow down, it disintegrated. The templates gathered dust, the pattern books closed, and the quarries fell silent, not for a season, but for a generation. To recognize these limits is not to diminish the achievement, but to understand its true nature. The medieval system for mass-producing construction materials was not a perfect, infallible machine from the future. It was a brilliant human invention forged within and constrained by its historical moment. It was a peak of organizational logic reached by a society that still prayed for good weather and feared the sudden arrival of a fever. Its triumphs in stone are all the more remarkable because they were accomplished not in spite of these vulnerabilities, but while navigating them every single day. The system stands as a testament to what communal human effort can build during a window of stability, and a sobering lesson in how fragile that window can be. It reminds us that our greatest structures are always, in the end, collaborations between the order we impose and the unpredictable world we inhabit. The walls themselves are the truest historians. To understand the medieval system, we must learn to read the language of the stones, a language of chisel marks and precise angles. This is the work of the architectural archaeologist, a detective who approaches a cathedral or a castle not as a monument of faith or power, but as a crime scene of construction. Their tools are not just trowels and brushes, but calipers, laser scanners, and a patient forensic eye. They begin with the most human trace, the mason's mark. By methodically cataloging every symbol on the hidden faces of stones in a single tower, they can map the workforce, A cluster of one mark might indicate the output of a single mason or a specific team. The distribution of marks can reveal how labor was organized, perhaps one crew assigned to the lower courses and another to the upper walls. It tells a story of parallel production lines, of quotas met, and of individual accountability etched in stone for centuries. The search for the module is a process of mass measurement. An archaeologist might spend weeks with a tape measure, recording the length, width, and height of hundreds of seemingly identical bricks from a medieval town wall. When they plot these measurements on a graph, a pattern emerges. The numbers do not scatter randomly, they cluster tightly around specific dimensions, say 11 inches long, 5.5 wide, and 2 1/4 thick. This clustering is the ghost of the wooden mold. It proves the existence of a standard, a communal agreement on size that was enforced not by chance but by system. Finding that standard module is like discovering the foundational unit of a lost currency, the basic coin from which an entire economy of form was built. Tool marks are another silent narrative. The broad, rough gouges of a quarrying pick give way to the finer, parallel grooves of a drafting chisel used for shaping, and finally, the smooth, polished finish left by a toothed claw tool. By reading this sequence of scars on an unfinished block or a discarded mistake, researchers can reconstruct the exact steps of the manufacturing chain, from rough extraction to final dressing. They can see where a template was held against the stone, where guidelines were scored, and sometimes where a worker made an error and abandoned the piece. These discarded stones are particularly precious, for they are snapshots of the process frozen in mid-action, revealing the techniques without the filter of a finished, perfect product. Perhaps the most vivid evidence comes from rare discoveries of the workshops themselves. In the shadows of great buildings, archaeologists have found the compacted earth floors of masons' lodges, littered with stone chips of a specific type. They have uncovered pits filled with the debris from carving a particular style of window tracery. In a few extraordinary instances, they have even found fragments of the wooden templates themselves, preserved in waterlogged conditions. To hold a piece of 800-year-old oak, still bearing the carved curve that defined 10,000 archstones, is to touch the system directly. It bridges the gap between the abstract idea and the physical mountain of masonry. All this evidence converges on one undeniable conclusion: the breathtaking regularity of a Gothic arcade, the perfect grid of a brick facade. These are not merely aesthetic choices or the happy result of skilled craftsmanship. They are the direct physical imprint of a controlled and repeatable production process. Each building is a fossilized moment in an ancient industrial workflow. The cathedral is not just a place of worship, it is a vast ledger of labor, a storage device holding petabytes of data about medieval society, technology, and economy. We need only learn the code to read it. This forensic reading changes our entire perception, shifting our gaze from the soaring whole to the humble, repeated part, and in doing so, it reveals the ingenious mind that connected them. The mason's mark on a European cathedral tells only one chapter of a much larger human story. This drive to systematize, to build vast complexity from simple, repeatable parts, is not a uniquely Western phenomenon, but a recurring echo across civilizations, each solving the same fundamental puzzle with the materials and genius at hand. Look to the domed heavens of the Byzantine Empire. In the great church of Hagia Sophia, raised in the 6th century, the builders employed a sophisticated layering system. They alternated courses of standardized brick with bands of mortar thicker than the bricks themselves. This was not haphazard. The brick dimensions were consistent, and the thick mortar joints acted as flexible cushions, allowing the immense earthquake-prone dome to settle and shift without catastrophic cracking. It was a modular system for managing monumental forces, a template for resilience written in clay and lime. Far to the south and east, the Islamic world achieved a different kind of perfection through precision. Walk into a medieval Moroccan madrasa or a Persian palace, and your eye is lost in a kaleidoscope of color and shape, a mesmerizing mosaic covering every surface. This is zellige, an art form of breathtaking complexity that is, at its heart, a triumph of radical standardization. Artisans first glazed ceramic tiles in a palette of perhaps 10 or 12 colors. Then, using hardened metal templates, they cut these tiles into a strict catalog of geometric shapes, primarily stars, crosses, and polygons. Each piece was a standard component, an immutable fragment of a larger mathematical language. The master craftsman's genius lay not in carving unique tiles, but in composing with this finite set of immutable pieces, arranging them according to geometric grids to create patterns that could theoretically repeat to infinity. The wall covering was in essence a mass-produced kit of ceramic parts, assembled on site into a unique and spiritually resonant whole, symbolizing the infinite nature of creation through the repetition of finite, perfect forms. Meanwhile, in China, a parallel evolution was unfolding in wood. For millennia, Chinese builders constructed towering pagodas and vast palace complexes using the dugong bracket system. This was a modular universe of interlocking wooden pieces, standard beams and brackets carved to precise templates that allowed them to slot together without nails. The entire weight of a heavy tiled roof was distributed down through this resilient, prefabricated wooden skeleton. The system was so standardized that the proportions of every hall, the spacing of every column, could be described using a basic module, often the width of the bracket itself. This meant a master builder in the capital could design a temple, and craftsmen in a distant province could prefabricate the wooden framework using the same manual of standardized joints, shipping it ready for assembly. Each of these cultures, Byzantine, Islamic, Chinese, faced the same core challenge as the medieval European mason: the need to build ambitiously within the constraints of pre-industrial energy, transport, and labor. Each arrived at the same brilliant, inevitable conclusion. They invented their own versions of the template and the module. They standardized their fundamental building blocks, whether brick, tile, or timber. This comparative view does not diminish the European cathedral. It elevates the entire conversation. It reveals standardization not as a single historical invention, but as a universal principle of human ingenuity, a logical and recurring solution whenever a society strives to translate a grand vision into physical reality at scale. The specific language differed: the vocabulary of the pointed arch, the muqarnas vault, or the curved pagoda eave, but the underlying grammar of repeatable, interoperable parts was strikingly similar. This places the clamor of the medieval quarry and the quiet discipline of the guild within a truly global story, a testament to our shared human impulse to bring order to chaos and to build our greatest dreams one perfectly measured piece at a time. The geometric precision of the medieval mason's lodge did not vanish with the last Gothic spire. It simply changed its clothes. As Europe emerged from the crises of the 14th century, a new intellectual wind began to blow, one we call the Renaissance. This era is often celebrated for its rediscovery of classical art, its focus on the individual genius, and its breathtaking paintings and sculptures. But beneath this flourishing of individual talent, the old, systematic bones of the building trade remained stronger than ever. The shift was one of emphasis, not eradication. Where the medieval master thought in terms of pragmatic geometry, solving immediate structural problems with compass and square, the Renaissance architect began with theory. He looked back to the Roman writer Vitruvius and his ideas on perfect proportion, believing that buildings, like the human body, should follow ideal ratios to achieve beauty. This was a humanist vision, placing man at the center of a harmonious universe. Yet, to translate that beautiful theory into brick and mortar, he still needed the same unglamorous tool: precise, repeatable measurement. The ideal proportion of a Palladian villa's facade was still expressed in numbers, and those numbers still had to be communicated to the stonecutter's template. The system adapted, absorbing this new layer of philosophical intent while retaining its core mechanical logic. The real revolution in dissemination came not from a new idea, but from a new machine, the printing press. The handwritten pattern book, once a rare treasure carried by a traveling master, was now mass-produced itself. Architectural treatises by thinkers like Leon Battista Alberti or Sebastiano Serlio rolled off the presses and into the libraries of nobles and merchants across Europe. These books did more than spread pretty pictures, they codified standards. Serlio's books, for example, presented the 5 classical orders of columns not just as history, but as a set of rules with every proportion, every molding detail meticulously prescribed. A builder in England or Poland could now purchase a volume and have an authoritative, standardized guide to the new Italian style. This accelerated the spread of architectural fashion to a dizzying speed, creating a truly pan-European visual language for elite construction. The template was no longer just a piece of wood in a local lodge. It was a diagram in a book that could be copied 1,000 times over. Yet the most profound legacy of the medieval system was not in the style of the columns, but in the organizational mindset behind them. The Renaissance and the early modern period that followed inherited something far more valuable than a set of techniques. They inherited a culture of large-scale project management. The cathedral building yard had been a laboratory for complex logistics, for managing multi-skilled workforces, for sourcing materials across great distances, and for enforcing quality control over years or decades. This hard-won knowledge, this institutional memory of how to make big things happen, did not fade. It was repurposed when the city of Venice needed to divert rivers to save its lagoons in the 16th century. The engineers who planned those monumental hydraulics projects were thinking like master builders. They broke the problem into phases, sourced specialized materials, and managed vast crews, applying a medieval scale of organization to a new kind of earthly challenge. This bridge is direct and unmistakable. The mindset that carefully coordinated the quarrying, transport, and assembly of 10,000 identical stones for a cathedral is the direct intellectual ancestor of the mindset that, 2 centuries later, would coordinate the digging of a continental canal. It is the precursor to the teams that would lay down thousands of identical iron rails for a railway, and later to the managers who would design the first moving assembly lines for automobiles. The core principles were identical: modular design, standardized parts, specialized labor, and precise logistical sequencing. The Industrial Revolution did not invent systematic production. It simply supercharged it with new sources of energy, steam and coal, and new materials like wrought iron and eventually steel. The conceptual blueprint, however, had been drawn centuries earlier on the tracing floors of Gothic lodges. We can hear a faint echo of the mason's mark in the part number stamped on a Model T component. Both systems designed to ensure accountability and interoperability in a vast collective product. So when we stand in awe before a great Renaissance palace or a soaring Baroque church, we are seeing a fusion, the marriage of a new artistic ideal with a very old, very reliable way of getting things built. The grandeur speaks of humanism and the power of princes, but the sheer fact of its existence speaks of a quieter, more persistent victory, the enduring power of a system. That system, born from the urgent needs of the medieval world, proved to be infinitely adaptable. It provided the essential groundwork, the managerial and logistical grammar, that allowed humanity to dream bigger and bigger dreams from the Dome of St. Peter's to the iron bridges of the 19th century. The cathedral was, in a very real sense, the first great factory, and its lessons written in stone became the first draft of our modern world. That ancient system of templates and guilds is not a relic, it is a mirror. Look at the world around you right now. Every device you use, every road you travel, every package that arrives at your door is made possible by the same fundamental principle. We have simply traded the wooden template for the digital blueprint and the guild ordinance for the international standard. Our modern world runs on a hidden lattice of codes and specifications, from the universal thread pattern on a light bulb that lets you replace it anywhere on Earth, to the standardized dimensions of a shipping container that seamlessly moves from a freighter in Shanghai to a train in Kansas. The medieval mason would instantly understand the logic behind a microchip, a product of unimaginable complexity built from billions of identical, perfectly placed transistors, the ultimate expression of mass production through precision. This historical echo reveals a profound truth we often miss. Standardization is not the enemy of creativity or progress, it is their essential foundation. It is the stable platform that makes daring leaps possible. The Gothic architect could experiment with gravity-defying vaults precisely because he could rely on 10,000 perfectly ordinary, identical stones to build them. In the same way, a modern software engineer can create a revolutionary application because she can rely on the standardized protocols of the Internet and the predictable architecture of operating systems. The system handles the repetitive, the foundational, freeing the human mind to solve the new problem at the edge. This is the first great lesson from the medieval quarry. Systems do not crush ambition, they channel it. They translate vast, collective dreams into a series of manageable, executable steps. Think of the global effort to develop vaccines in recent years. The monumental goal was shared by thousands of scientists and nations, but it was achieved through a framework of shared data standards, clinical trial protocols, and manufacturing regulations. These were the modern guild rules, the agreed-upon templates that allowed a decentralized, global network to produce an interoperable solution at a speed that would have been otherwise impossible. The medieval cathedral and the modern vaccine both stand as testaments to what humanity can achieve when we agree on the rules of making, and then empower individuals to build within that framework. As we stare down our own era's monumental challenges, from providing affordable housing to rebuilding aging infrastructure and creating sustainable cities, we are searching, just as they did, for the key to scaling solutions. We instinctively hunt for the new miracle material, the futuristic technology that will solve everything, but the medieval model whispers a different, perhaps wiser, strategy. Their breakthrough was not a new type of stone, it was a new way of thinking about all stone. Their revolution was logistical, not material. They looked at the same limestone their ancestors had used for centuries and asked a different question. Not how do we carve this better, but how do we organize its carving? How do we design, produce, transport, and assemble it with such efficiency that we can build mountains of it? This is the urgent lesson for our time. The path forward in sustainable construction may lie less in inventing a magical new carbon-neutral concrete, and more in perfecting a system to use vastly less concrete overall, through modular design, prefabrication, and the circular reuse of materials. It is about building smarter, not just building new. The true legacy of those medieval builders, therefore, is not in the stones they left behind, but in the mindset they perfected. It is a lesson in the power of shared rules to build a common world. Their cathedrals and city walls were physical manifestations of a social contract, an agreement on how to work together to create something larger than any one person or lifetime. In an age often focused on individual expression and disruptive innovation, their story reminds us of the quiet, collective genius of the system, the framework that turns isolated effort into civilization. It asks us to consider what shared templates we need to design today, not for castles, but for a stable and flourishing future for all. That quiet revolution in stone and clay echoes in every modern street and skyline. The medieval world did not just build cathedrals and castles, it built the very grammar of construction, a language of parts and processes that we still speak today, even if we have forgotten the original words. From the anonymous quarryman matching his chisel to a wooden template, to the guildmaster enforcing a standard brick size, they mastered a holistic system, a complete ecosystem of making that seamlessly wove together design, production, logistics, and economics. This was not a constraint on creativity, but its greatest enabler. It was the liberating framework that turned impossible ambition into enduring stone, allowing a society to dream in monuments and wake to find them built. The soaring Gothic arch is not merely a triumph of faith or engineering. It is the ultimate proof of concept for a pre-industrial system of mass production. Every precise curve is a testament to the template, every repeating bay a celebration of the module, and every surviving wall a monument to the human ingenuity that organized chaos into a reliable, repeatable process. So the next time you walk past an old stone wall, perhaps in a historic city center or even in the countryside, do not just see weathered rock and crumbling mortar. Look closer, see the subtle rhythm in the coursing, the consistent size of the blocks, the ghost of a standard. You are looking at the physical expression of a sophisticated system, a frozen moment in an ancient, highly organized workflow. That wall is a story written in the language of standardization, a language that allowed our ancestors to build a world that still shelters, inspires, and teaches us centuries later. If this journey into the hidden systems of the past has sparked your curiosity, we would love to hear from you. Which medieval structure, whether a humble parish church or a soaring cathedral, leaves you most in awe of the hands and minds that built it? Share your thoughts in the comments below, and if you are eager to uncover more of history's quiet revolutions, the ingenious frameworks that shaped our world from the shadows, be sure to subscribe. Our next exploration into the hidden systems of history awaits.